Welcome to the section on validation and testing. We shall see in the section that evaluating a model's performance based on solely the training data set or based on the data on which the model was trained is actually a very wrong practice. Supposing we have a data set which comprises of inputs like this, where we have the class R's, the quiz mark, and the final mark, and then with an output, the status, which depends on these three inputs. If we train our model on this full data set and we evaluate it based on its performance on this whole data set on which it was trained, there are great chances that we don't know exactly how this model will perform when presented new data. In practice, when given this kind of data set, what we tend to do is we break this data set into several parts. Let's suppose initially we break the data set into two parts. The first part will permit us train the model, and with the second part, we'll be able to evaluate the model based on data it has never seen. And this is very important to ensure that we are not evaluating the performance of that model based only on data it has seen. So this means that if we have two models, say A and B, and that model A performs extremely well, supposing an accuracy of 99%, and then model B has an accuracy of 95%, but then if in the validation set, or if in supposing another data set which doesn't contain the points which were used to train the model, we evaluate A and we see that its accuracy drops to 70% while B's accuracy drops maybe to just 80%, we could come to a conclusion that working with model B is better, as it could generalize on new data it has not seen. In general, we don't just split our data set into two parts. We split our data set into the training, validation, and then the testing blocks. This simply means that if we have this data set, firstly, we shall shuffle it to make sure the data is evenly distributed. Then we shall break it such that we have a part which is the training, which we shall use for training. Then the part which we shall use for validation is what we shall use to select the best model suited for our problem. So that means when we have a problem, we have the training and the validation performance, which is to be measured. So given this model with these three inputs and an output, after training, we measure the training and the validation performance. Note that the validation data set wasn't used to train the data. So this is some sort of new data to the model, although it belongs to the data set. So that said, after training for model 1, we have the training and validation performance. Model 2, we have its training and validation performance. And then model N, we have also its training and validation performance. So as we could see, the validation data set helps us validate our model's performance. And then after validating the different models' performance and then picking out a given or best model for our problem based on the training and validation performance, we now go ahead to test this data or to test our model's performance on the testing data or the test data set, which clearly is an unbiased way of testing our model. So that said, let's see the way we generally split the data set. Let's suppose we have a number of data points to be 1,000. So supposing this data set has 1,000 data points. By data point, we mean the inputs, that's 3 inputs and 1 output. So this is 1 data point, this is the second data point, up to say the 1,000 data points. In this kind of examples where the number of training examples or the data set isn't very large, we could pick out the percentage of training data points to be about 70%, and then the percentage of validation about 15%, percentage of test data points about 15%. Now we could always tweak this to suit our problem. So we could have, say, 60%, 30, 10, or 60, 20, 20. Now in this example, we've taken 70%, that's 70, 15, 15. Now 70% of 1,000 is 700, so we're training on 700 data points. We're validating on 150, and then we're testing on 150. But also note that this kind of data sets are not very common, and we have to do our best to avoid this kind of data sets. And by avoiding simply means we have to gather as much data as possible, because the more high quality data or the more representative data we have, we could be able to train a model which actually represents that data correctly. Now let's take another example where we have a number of data points, say 100 million, which is very typical in deep learning. Here we will have the percentage of training data points. We could take it to be 96%. Here we have 96 million training data points. And then for the validation, we could take 2%. You see that this percentage, which is 2%, gives us 2 million data points. And this 2 million clearly is way more than even the size of the training data set here. And that's why the more data points we have, we could afford to reduce the validation set, because reducing the validation set percentage on the overall data set will still yield a considerable number of data points. Then we could pick for the test data set 2%, so that's 2 million data points. And so with this, we understand clearly that it's actually useless for us to measure the performance of our model based only on data it has been trained on. Another common error which could be done when breaking up our data set into the training, validation, and test data set would be to take the training and validation data sets, or the training and testing data sets, from two different distributions. By two different distributions will simply mean that we may do the splitting such that the samples or the training samples are quite different from the validation samples. Let's take a simple example. Supposing that we have the first 700 data points in our data set, which are made mostly of examples in which the status is 1, and that the last 300 are made mostly of examples where the status is 0. This means that if we split our data set naively, that's without doing any shuffling, then the first 700 will be for the training, then the rest for the validation and testing. And this means that our model will learn instead how to better predict examples where the status has an output of 1. And hence, when this model will be presented with data now in which the status is meant to be equals 0, this model wouldn't perform very well. So to avoid this, from the onset, we have to shuffle our data set before doing the splitting.